Today we're going to be evaluating integrals, double integrals, over some general regions that are very much different from the previous day in that they are not rectangles. We're going to have two types, a type 1 and a type 2. You can see at the top of the page, plane region D is of type 1 if it lies between the graphs of two continuous functions. And that would be with x bounded between a and b, y is bounded between two functions, g1 and g2. There are several pictures that represent this type of a possibility. One common theme that I hope that you'd see is for all of these regions, if we were to draw a vertical segment, you could see that very clearly that y would be bounded. There is a definite top y value and a bottom y value, always defined by that top function and the bottom function, g2 and g1 specifically. Whereas as we look at x would just go between a and b. Notice how we're going to be able to write this integral out. We're always going to begin integrating with respect to y in a type 1 type of a region. We will immediately deal with those boundaries that are containing y, and finally then we will integrate with respect to x from a to b. The end result will be a real number, perhaps a positive or a negative real number. Very quickly, you might wonder if it's very possible that instead of having a boundary for y, if there might be a boundary for x. And indeed that would be the case. This is what we would call a type 2 region, where y is bounded between two real numbers c and d. However, x, and we could draw a horizontal line at this point, x would be contained between two functions, h of 1 of y and h of 2 of y. h of 2 of y would be the larger, and this of course would correspond to the upper bound. h of 1 of course is the smaller. And really we're just going to investigate several types of problems where we can see this. So let's just immediately get started here. Always draw D. That's so important. You want to sketch this out. You can see that D in this problem and all these problems here will be written as a subscript underneath the double integral. We're saying we are integrating over that region. And D is bounded by two parabolas. We have 2x squared that's going to be centered, or having a vertex I should say, at the origin. Y equals 2x squared. We also have 1 plus x squared. That would be over here. And you might guess that those two curves are in fact going to intersect. You can see that 2 is going to be a lot more narrow than what we'd have for a 1 out in front of x squared. Very quickly, if we set those two y values equal to each other, it would not take you long to solve and see that x squared would equal 1, or x would be equal to a plus or a minus 1. So we could see very clearly that x would be bounded between -1 and 1. But look at this. I hope everyone would be able to say quickly this would be a type 1 region, because we could draw a vertical segment anywhere in this region, and always realize that our y values are bounded between this top function of 1 plus x squared, and then down below by y equals 2x squared. So how could we write this integral up? Well, again, beginning with the boundaries affecting y. We have 2x squared to 1 plus x squared, and of course our integrand is x plus 2y. And then of course we would be integrating from -1 to 1 as well. Right now we can move beyond just saying that we have d of a and just specify that we start with dy. And as we are integrating with respect to y, the derivative of x with respect to y would be xy, and the derivative of 2y would be y squared. And then of course we're going to be substituting in a 1 plus x squared and a 2x squared down below. Now this, I hope, is pretty evident that it's going to be a little bit more work to work these out. But again, we're using the fundamental theorem, substituting these boundaries in wherever we see a y. And here we have 1 plus x squared, quantity squared. Then on top of that, we're going to subtract, plugging in 2x squared for our y. This would become a 2x cubed. I hope everyone would see. 2x squared squared would be a 4x to the fourth. And of course, don't forget, we are not done with the problem. We still have to integrate. But let's clean this all up. This will become x plus x to the third. If we were to expand all this out, I hope everyone would agree, it's 1 plus 2x squared plus x to the fourth. And then we could say minus 2x cubed and a minus 4x to the fourth right here. Definitely a little bit messier than what we saw yesterday. But let's combine our like terms. You can see that in this integral, we're still going to have a constant. We have a 1. With x's, well, it looks like we only have one term with an x. That's a plus x right here. With x squared, I just see a plus 2x squared. With x cubed, we have an x cubed minus 2x cubed. That would become a minus x cubed. With our x to the fourth, well, a 1x to the fourth minus 4x to the fourth is a minus 3x to the fourth. And at this point, we're virtually done. We're back to a problem that we've seen many, many, many times before. All we have to do is just continue to integrate. Antiderivative of 1 is an x. This becomes x squared plus, well, bump this up. It's 2/3 x to the third minus x to the fourth over 4. And then minus 3/5 x to the fifth, and then just apply our fundamental theorem. Well, plugging in a 1, well, we'd get 1 plus 2/3 minus 1/4 minus 3/5, and then we will have to subtract, plugging in a negative 1. Well, this would be a negative 1. Negative 1 squared, of course, is just going to become a 1 itself. Negative 1 cubed, well, that's going to become a negative 2/3. Negative 1, when we raise it to the fourth, is still going to be a positive, but we still have the minus out in front. That's going to be a minus 1/4. From here, negative 1 to the fifth is a negative value. That would come out and make that a plus 3/5. Well, of course, we can immediately look inside that second parenthesis and know that 1 and negative 1 are going to cancel out. We can distribute some negatives here and see what happens. But before we even begin to try to combine like terms, with the fractions especially, let's just see what might happen if we distributed this negative everywhere. Negative 2/3 is another plus 2/3. This would be a plus 1/4, and a negative 3/5. Well, that would make that as so. 1/4 and negative 1/4 are going to cancel, and then 2/3, of course, will really become a 4/3. Negative 3/5 and another negative 3/5 is a negative 6/5. Well, it's getting better. Let's turn this all into 15ths. That would be 30 over 15 plus, let's see, multiply by 5. This is 20 over 15. And this would be minus 36 over 15. Well, 30 minus 36 is negative 6. Negative 6 plus 20 is 14. Final answer, 40/15. Okay, so that's how we do a problem as such. Let's real quickly take a look at this next problem. It says find the volume of the solid lying underneath that paraboloid, above region D, where region D is bounded between the line y equals 2x and the parabola y equals x squared. Well, y equals x squared, of course, is going to be a parabola opening upwards, having its vertex right there at the origin. And y equals 2x, well, y equals 2x is also, of course, going to have the point 0, 0 on it. But of course, as we just draw that up here, you can see that our line is going to cross somewhere over here. We can solve for where these two curves are going to cross. Set 2x equal to x squared, and we can subtract a 2x. We can factor out an x, and then we get x minus 2. So you can see very quickly x equals 0, x equals 2 appears to be where we intersect. Now immediately I want to point out that this is still another type 1 kind of a region. As we look at that boundary, we can see that the line is always up on top, the parabola would be down below. So what we could do immediately is say, well, I'm going to integrate. Down below we have our parabola. Up on top we have our line, that's 2x. And we're going to be integrating between 0 and 2. But we've got, here's x squared plus y squared. And we're going to go first with respect to y, then with respect to x. Well, let's do this real quickly. Antiderivative with respect to y. Here we go again. This will become x squared y plus y to the third over 3. You can always double check if you're right by doing a real quick derivative. Well, right now let's use that fundamental theorem, plug in our 2x, and as we do we'll have x squared times 2x. You can just put that all together right now. That's going to be a 2x to the third. 2x cubed is going to be 8x cubed. So that's 8x cubed all over 3. And then we could say subtract. We'll plug x squared in for y. X squared times x squared is x to the 4th. And x squared cubed is x to the 6th. So we'd get x to the 6th all over 3. Well, we're almost there. You can see right inside the first grouping that 2x cubed, if we got a denominator of 3, would be 6x cubed over 3. So this integral will become 14x cubed all over 3 minus x to the 4th plus x to the 6th all over 3. Wow, we're getting there. We're getting close. Antiderivatives. Let's see, bump this up to x to the 4th. That means also divide by a 4. Well, 14 all over 3 times 1/4. Well, a 2 goes in and a 2 goes in here. You'd have 7 over 6. That's 7 over 6. Bump this up, you get x to the 5th all over 5. Bump this up, you get x to the 7th all over 21. Now, thank goodness with a bound of 0, you can see really quickly that some good things are going to happen. Plug in your 2, though. 2 to the 4th is actually going to be 16. So you'd have 7 over 6 times a 16. We'll clean that up in a sec. 2 to the 5th is 32, so that's 32 all over 5. And let's see, 2 to the 7th is actually 128. 128 all over 21. And even right now, you know, you definitely could do some cleaning up and just get some help with the calculator. Let the calculator finish this problem up for you if you need to. We know that dividing out a 2, though, there's a 3, here's an 8. So there's 56 thirds minus 32 over 5 plus 128 all over 21. Okay, so punch that out. 1,928 all over 105. So 1,928 all over 105. Okay, that's all we've got time for right now. We've got one more problem that we're going to have to wrap up.